So let's get going. Welcome everyone to College of Science virtual seminar. Very excited today to welcome Bob Miller, who is a longtime faculty member in the geology department in our College of Science. Just a little background on Bob. Bob got his bachelor's degree in geology from Allegheny College. Then a master's in geology at the University of Washington and a PhD in geological sciences at University of Washington, doing studies of some of the myriad pieces of mountain range in Washington itself. Great place to study active geology. He held teaching positions at University of Washington, University of Kansas, and Clark College before joining San Jose State in 1984, where he's been ever since. He's also had visiting professorships at the University of Durham in the UK, MIT, and at James Cook University in Australia. He's been a consultant on a number of studies with federal agencies and private companies throughout the Northwestern Washington area. He's currently an associate editor of the journal Geosphere, and has done a number of other journal editing jobs over the years, including being very active in the Cordilleran section of the Geological Society of America, and he's a fellow of the Geological Society of America. Bob today is going to tell us about what happens when an oceanic island like Iceland collides with a continental margin. And I'm very, very excited to hear about this fabulously powerful and weird timescale and size scale collision. As usual, if you have questions for Bob, go ahead and type them in the chat or the Q&A. I'll be monitoring those throughout the talk. If it looks like something I should interrupt Bob for clarification, I will. Otherwise, I'll leave the question for you to ask at the end of the talk. So Bob, without further ado, take it away.
Oh, thanks, Michael. Yeah, it should be fun to talk about some of the work that I've been doing with colleagues on a project that's lasted over the last 6-7 years, as well as a number of San Jose State masters and undergraduate students. Some of the students are listed here. As I say, this was a truly collaborative project, which has involved geochronology by my colleague and late colleague Sam Bowering at MIT, and Mike Eddy, produce lots and lots of high quality ages, which have really made our field relations help with the field relations and trying to synthesize things. Jeff Tepper at Puget Sound and Paul Umhofer at Northern Arizona and their students have also been part of this. So it's been a pretty big effort, and it was good timing to do this talk because we're trying to put together a synthesis, or I'm supposed to be finishing the paper off soon. The usual soon being somewhat undefined. Anyway, so I'd like to talk about our group results. And I'm just going to start out with a GE level slide that we use in almost all of our intro classes. So this would be just looking at a standard plate tectonic model with an oceanic spreading ridge and a trench and a magmatic arc with volcanoes and plutons, that sort of thing. But there's one aspect that I want to emphasize in the beginning, and we will talk more about what happens at subduction zones. And these are hotspots, which are thought to be stationary or relatively so compared to the movement of plates. They're typically thought to come from near the core mantle boundary in the lower mantle, although there is some debate on this. But because they're relatively stationary, we used to think they were stationary, but they do appear to migrate. These hot spots or places where mantle plumes move up and melt provide a good sort of marker and lead to some interesting features. So here, this would be the sort of standard model for Hawaii, where you're within an oceanic plate, not at a plate boundary, but where the volcanoes form in the middle, and say in the case of Hawaii, in the middle of the Pacific. So if we look at the major active hotspots, we do have, again, Hawaii, a number of them in the southern Pacific. The Azores and Iceland are a couple that are interesting in that they are forming on a mid-ocean ridge. So not only do you have the oceanic ridge where oceanic lithosphere is formed, but there's also this hotspot, which tends to produce a large volume mass, such as the case here in Iceland, where you have the combination both of the hotspot and the ridge, and you can see you have this big oceanic plateau. The Canary Islands down here, which have been in the news lately because of the active volcanism, would also be, would be more like Hawaii, would be in a plate. In terms of continental ones, the one, again, that's probably best known on the planet, and one that we talk about in intro geology classes, is Yellowstone, and that's going to be a important part of our story. All right, so one of the things these do is they do form these hotspot traces. So most of you, again, this is the one that's used in the textbooks, where the Hawaiian, the active hotspot is beneath the big island of Hawaii, and you can trace this out to the Emperor Seamount chain to the north. Interestingly, you see this big bend in the chain, which happened in the Eocene, which is the time period that I'm going to actually be talking about in the Pacific Northwest. It's a period of time in which a number of major tectonic events happened around the globe, really. Himalayas as well, the initial collision or parts of the collision of the Indian subcontinent with Asia occurred then. There are other examples where the hotspot trace goes from the ocean onto land. One for the many people know about, perhaps, or some people would be in the Atlantic with the Kelvin seamounts, which go on to land to form the White Mountains intrusive suite, which is part of the reason why the White Mountains are so high in New Hampshire. All right, and so one we're going to come back to is the Yellowstone hotspot trace. So here's a diagram from a recent paper, and Yellowstone's pretty clear. The Snake River Plain coming down through, say, Twin Falls and Boise, that area is pretty clear. Things are more complicated to the southwest, but overall, it appears you can trace it at least back to about 42 million years, or 40 and a half, where it overlaps it overlies what's called it's a Tillamook stage. So Tillamook's in northern Oregon on the coast, Tillamook cheese, etc. And so the hotspot tracks back into this terrain that I'll be talking about called Silesia. Okay, so let's look at a little bit at our back to our standard plate tectonic model. There are a couple of other things now. We talked a bit about developing a hotspot and that this can occur on a ridge, but I also want to look a little bit at our convergent plate margin. So this is the kind of margin we had in California and what we have in the Pacific Northwest from certainly from about 100 million years ago until 50 million, and then a change, and now we have it today with the modern cascades. So if we look at this, this is our standard model generating magma above the downgoing oceanic plate at, say, 100, a little over 100 kilometers depth. But what happens if there is buoyant or very thick oceanic lithosphere that comes into the subduction zone. And what is generally can be shown by modeling is that if the crust is either really hot, or the slab that's being subducted is really hot and hence buoyant, or is very thick, it will thick and low density, relatively low density, it will not go down the subduction zone as at steep an angles. So it flattens out, or what we call flat slab subduction. It still does dip. And this is the model that I've taken a figure for California at about 80 million years ago, when it's thought that an oceanic plateau entered the subduction zone off of a little south of here. And what it did was the subduction zone flattened out. And because melting is driven 100 to 150 kilometers depth, when the slab is at that depth, naturally with a gentler dip, magmatism occurred much farther inland, and the Sierra Nevada batholiths shut off. So that's the scenario there. And we're going to see that something similar probably happened in the Pacific Northwest at a little younger time. Hence the reason I'm showing this. All right. So again, you have this coming close to the, you have thickened crust being subducted. But then what happens when the actual ridge actually reaches the trench? All right, so it's reached the trench, and you might expect, okay, a ridge enters the trench, that's going to cause a major reorganization, and this is indeed what led to the San Andreas fault. But what happens if it's got a big oceanic island on it, like Iceland? So this is one of the things I'll be exploring in a few minutes. All right, so let's look again at this some of these complications, such as what happened when the San Andreas reached the East Pacific Rise reached the trench to form the San Andreas in California. So what this diagram is trying to show is here's an oceanic ridge, and there's two oceanic plates. This is the relative convergence between the oceanic plate and the overriding continental plate. But what I want to draw your attention to is that where the ridge hits, there's no longer going to be generation of new oceanic lithosphere by uprising of hot mantle. And so what happens that is coming from, continuously from the ridge, is the plate goes down, it's diverging, but it's not, the plate isn't growing because new magmatism to form the ridge is not occurring. So this is called a slab window, such as you see here, the white area being the slab window. Now, interestingly then, or what the complication is that as the slab, the downgoing lithospheric slab, essentially gets a hole in it or a window in it, underlying still hotter mantle, the asthenospheric mantle, it's called, rises up. And as it rises up, it begins to heat the overriding plate. And so that induces melting, but it may induce melting west of where, or outboard, excuse me, of where an arc was. So in the case of California, this explains, or partially explains, why we have young volcanics, say in Henry Coast State Park near Morgan Hill, or why we have the geysers farther north, or volcanics near Calistoga. So we're talking about areas which should be cold geothermally, yet there are volcanoes and intrusions occurring way outboard of what's the arc. So this is this sort of anomalous so-called near trench magmatism is a real hallmark of when a ridge subducts. A couple of other things to note is that ridges are offset by transform faults. We see this just any map of the ocean floor. And what that means is that when a ridge might come in a segment and get subducted here, you can see it's going to cause the triple junction to migrate, much like the Mendocino triple junction in California is progressively migrating northwards. It's obviously reached Mendocino now, but it will continue to migrate, presumably. And but eventually this little segment will get subducted, and then the ridge will jump, or then there'll be a jump because of the transform. You still be subducting material until this ridge segment comes in, then there'll be another jump. The point being, it doesn't happen all at once, that there'll be this migration of things. And as a result, like here, it's showing what they call a four-arc sliver, and that's because the spreading or the stretching here, extension here, is driving part of the overriding plate as well. So we have a lot of complications. There's other things shown in this sort of textbook diagram, or not standard textbook, but on this diagram. But I think you get the general idea. Things are going to be messy. All right, so let's step back then and move to the Pacific Northwest and look at a couple of scenarios that have been proposed for the plate setting. Most everyone agrees that at 60 million years or about that an ocean ridge intersected the continental margin in southern Alaska. And the traditional way of looking at this is it's the Kula plate, which is largely gone, and the Farallon plate, named after the Farallon Islands. The Farallon plate, there's still little vestiges of it in terms of the Juan de Fuca plate off Oregon and Washington and Northern California. So this was a Farallon plate. They're subducting beneath North America. Here's the ridge intersecting. And in this model, there's at 60 million years, if we look at the Pacific Northwest, it's a normal subduction zone. In the other model, there's a plate which is now gone, resurrection. It's called the resurrection plate. It's based purely on the on-land geology. And this proposes that we actually have a ridge that's going to intersect around Vancouver Island getting close to it at 60 million years. And for our purposes, in our synthesis, either way, by 52 million years, there's a ridge right off Vancouver Island and northwesternmost Washington, which is convenient because it's very difficult to know which of these models is correct, simply because we've lost so much of the ocean floor. It's been subducted. Anyway, by 52 million years in either model, it appears likely that we had a ridge intersecting the trench. And even within our group, we don't all agree, and some are agnostic. Okay, so let's look at structures and rocks of Eocene age, let's just say for our purposes now, around 50 million years. And some of the main features I want to call your attention to, here are the outlines of the states, California down here. One is Silesia, which will be a focus of the talk. These are voluminous basalts that extend from southern Vancouver Island to southwestern Oregon. There are locations of near trench magmatism. That's the yellow stars that you see are areas where there is magmatism near the trench. There are also dextral right lateral strike slip faults, which is the same as the San Andreas dextral, easier to type. And call your attention to these strike slip faults that are of Eocene age, and also the location of metamorphic and plutonic rocks. So this would be the heart of the North Cascades, really between this fault, SCF, the Straight Creek Fault, and the Ross Lake Fault. And this was the area of an arc that was active back to about 100 million years, and which extends with basically volcanoes and plutons beneath that extended all the way to southeast Alaska and actually dwarfs the Sierra Nevada batholith in size. Okay, so we have those rocks. We also have some younger volcanic rocks to the east that I'm part of our synthesis. So I'm using these diagrams. We don't really don't have time to go into all the details on this. So I'm largely going to restrict relationships here to over here in terms of our discussion. All right, so let's start looking a little bit at Silesia. Silesia is this province outlined in green, with the light green being where we think it is on the basis of geophysical data. It's very distinctive in terms of density and magnetic properties, so pretty confident on the location. The dark greens are where it's actually exposed at the Earth's surface. Silesia is made up of oceanic basalts, marine basalts. The crust is at least 25 kilometers thick in Oregon, and maybe as much as 35 kilometers thick of basalt. And that's very important because these are oceanic basalts. Typical oceanic crustal thickness, not just all, which isn't just all basalts, is 6 to maybe 8 kilometers. So we really have this tremendous volume of basalt extending for, about 600 kilometers or a little more north-south. And as you can see, probably on the order of averaging more than 50 kilometers across in an east-west direction. So tremendous volume of magma that was erupted on the Earth's surface, very, very thick. And when you look at the chemistry, it has mid-ocean ridge basalt chemistry, like an ocean ridge, but there are differences in some of the basalts. They're called ocean island basalts. They have different chemistry because they're generated by melting at different depths in the mantle. And this is very much like Hawaii. So again, this comparison to hotspot, it's generally agreed this makes sense to make this a hotspot, formed at a hotspot to account for the tremendous volumes and the chemistry. Also, then the final thing is many of us, or the majority of workers, not everyone, thinks it formed above the Yellowstone hotspot. And that's where the Iceland analog with the title comes in, that it would have been an ocean ridge, would have been a hotspot beneath an ocean ridge, forming a very thick mass. And there is evidence that some of it certainly was above sea level. So that's the big push on Silesia. I want you to keep that in mind. So now just going to step here, and it could take lots of time to go over this, but try and keep it simple. Here's where we've done most of our work as a group. Certainly not all of this, it's a huge tract of land. But if we look at this again, here's Silesia. Now we're focusing on Washington State. Here's Seattle to give you perspective. Vancouver would be just off the map. What you see here is these are the actual exposures of Silesia, changed colors, unfortunately. And you can see this was a boundary in the subsurface, goes through Seattle, and it's exposed on southern Vancouver Island, north of Victoria, if you know Vancouver Island at all. And here are some of the near trench intrusions and associated volcanics They come down fairly close to Seattle. And what you can see is these, again, are outboard or closer to what should have been the trench, because there should have been a trench between Silesia and the continent. And they're well west of where the arc in the North Cascades developed. Anyway, so we'll keep it at that for now. Here are the metamorphic rocks, the former arc. Here's Silesia, and there's a number of other units that we'll simplify and not talk about much. All right, and doing these kinds of reconstructions, one of the things that's really important to consider that I think we're the first to really do in terms of really thinking about this at a broad scale is trying to restore the strike slip faults. So I mentioned that there are a number of these right lateral strike slip faults. A few of the major ones are shown here. And what they progressively do is move rocks to the west, northward relative to the stable part of the continent, or even just let's just say rocks to the east. So if we look at it sort of a western belt or western zone out here, these rocks have moved a minimum of by our calculations, a minimum of 315 kilometers relative to, say, the rocks back here at the Washington, Oregon, Idaho, where they all come together. So restoring then the geology we were just looking at puts Vancouver Island down in modern day Oregon and moves Silesia down as well. So we have to do that. Then our central zone, I should point out sort of the ancient arc itself, that's about 125 kilometers relative to the eastern zone. And so there may be actually larger slips, but this is the stuff that we've constrained and mapping over the years. So I think that's where, even this is fairly conservative. All right, and then down below, just sort of shown what plate would be. We've taken use Kula. KR means it's Kula or resurrection. But anyway, we have this downgoing slab. We have this slab window developing, like I talked about, right where the ridge intersects the trench. And then over here, we have the Farallon slab, just like we have farther south. Okay, and then again, notice Silesia, this Yakutat's on here. Yakutat is, there's a bunch of basalts in southern Alaska that were probably part of this same hotspot oceanic plateau, but they were on the other side of the ridge from Silesia, so they have moved northwards. That's Yakutat basalts, the Yakutat terrain is collided with southern Alaska. That's why, or is colliding. That's why the mountains are so high. The Wrangell Mountains and St. Elias Mountains there in where Canada and I guess Yukon and Alaska border, where the peaks get up over 19,000 feet, are due to this big block of basalt moving northwards. The other key aspect, though, from this 55 million year time slice, and from 60 to 55 million, or 52 million really, is there's a magmatic lull. So in other words, the North Cascades and into southern British Columbia, was a site of active volcanism and plutonism, particularly plutonism, that is like the Sierra Nevada granites, that shut off at 60 million years. So there's this lull. And what we ascribe this to is the flat slab subduction that I mentioned earlier. And then if we move up a few million years in time, now we get to the period of the actual collision. And, as Michael said in his email, and here, this is an impressive collision. There's a lot of material. It's dwarfed by, say, a continent-continent collision, like was happening in the Indian subcontinent and the rest of Asia, but it's still a significant volume of material that doesn't really want to subduct, and so it collides with the margin. Now, what's the evidence for this? Again, we have the near trench magmatism, and that's what we show where the ridge is actually entering. But talk about in a minute, there's a big fold and thrust belt inboard of Silesia, which extends, as you can see, from around Roseburg, Oregon, to Vancouver Island. There's a basin that's exposed east, a very large basin that extends down when you restore it from just about the Canadian border at Bellingham, all the way down to central Washington. And this basin was subsiding and accumulating sediments, but then it became inverted. That is, it became uplifted. And we'll talk about one other aspect in a minute, and that is that magmatism began to roll back during this time, and go over what this means in a minute. But basically, the ages of magmas in Idaho and northeastern Washington start migrating, or the location migrates to the southwest. So lots happening, and there's more stuff to the east that I'm going to skip. All right, so let's look at this effect of the collision. So the collision, there's intense folding and thrust faulting, that is contractional or shortening faulting of the Earth's crust, well developed in Southwest Oregon. Going northwards, there's all these young volcanic rocks that bury things, so we don't know much about in here. In Silesia itself, there are a bunch of folds of basalts and overlying sediments, or interlayered sediments. And then we have more folds up here in Washington, and then the Cowichan is in southern Vancouver Island. So we have this long belt extending, more than 500 kilometers of intense shortening. Just to show you some pictures to break it up. Here are some of the metamorphic rocks in northern Washington, just showing a nice fold. This is Nikki Windsor, who did her master's thesis up here. And the migmatitic just means these rocks were partially melted. I'll briefly talk about them later on. But again, subhorizontal shortening, which we infer is related to the collision. You can see it on a larger scale on this cross section. So the scale 1,500 meters here. There's no vertical exaggeration. And this is just from our mapping. You can see this is just how the foliation or compositional layering in these metamorphic rocks are folded on a much larger, over much larger distances. So again, accommodating this collision. Now, I also mentioned that Plutonism, the magmatism, migrated in northeast Washington. So this is just a plot of reasonably good quality uranium lead ages on zircon. If you went to Jonathan Miller's talk last spring, he talked a lot about uranium lead geochronology. We'll just worry about the results and not the nitty gritty or the gory details. Anyway, if we go this way, you can see the ages going from Idaho to Washington progressively seem to young, at least if you look at the decent quality data. And this has been interpreted by one of my colleagues, Jeff Tepper at Puget Sound, as part of the project, is that this is due to slab rollback. And the idea of slab rollback is simply that the downgoing plate, if you look at this, the purple is time one, is the plate starts migrating as with time, it's migrating, in this case, from left to right, unfortunately, kind of opposite of what this figure over here shows, the map shows. But the general idea, gravity is causing this to sink. Once the ridge and Silesia reached the trench, you no longer, essentially the system stagnates, and the slab then begins to roll back, and melting above the slab then migrates with it, hence giving us this age progression. And then what other things we have? This at 49.5, again, the 45 resulting from this, there's this just major plate reorganization where now that Silesia is collided, there's no longer a trench here, but there's still forces in terms of moving of the Pacific or the Kula plates, oceanic plates. And so the subduction zone shifts or jumps outboard now, as opposed to being on the northeast side of Silesia, it's now on the southwest side. Because the triple junction now is here, where the three plates come together, you notice that the spreading direction, the movement direction, might make things migrate on the left side or west side, they'll migrate northwest, whereas they'll be subducted here. So what happens, and this ties in very nicely with our fault studies, is the faults either initiate or accelerate the right lateral slip. And then we get major dike swarms, which I'll talk about. The crust is, in a minute, essentially is getting pulled apart, broken apart. There's a very large, what's called a magmatic flare-up, where there's just really high fluxes, the highest addition of magma rate in the North Cascades that we have documented, and higher than present day, by much higher than present day Cascades volcanism. And this area in here, we call slab, and we'll talk about this, the slab, which is rolling back, begins to break and then tears. So again, this idea of dikes, I'll show what this means in a minute, but here just the red lines represent the orientations of dikes in areas of where they're particularly abundant, and the red dots sort of indicate this as well. So just to give you, this is again about the latitude of a little south of Seattle. And then this is the international border up here. So they're over a very extensive area. The important things about dikes, like this one, very thick one, by the way, compared to most. These trees, this is the Pacific Northwest, so these trees are pretty tall, at least 30 meters to give you a sense of scale. But the idea would be this dike represents a fracture which opened up and presumably perpendicular to the walls, and then melt came up through it. So this is commonly thought to record regional stress and strain, which is very useful for us. There are other mechanisms, but these do not seem to apply overall for the dikes and the Cascades. Again, here's from Shady Bryan, a thesis here. You can just see how pervasive these are. There's a scale, so we're talking about things in this Google Earth image go for at least a kilometer, and you can just see they're quite consistent, all these ribs of rock going through this area, which I don't know when the forest fire was, but which was burnt pretty significantly. So again, the extension would be perpendicular to the dikes, or in this case, west, south, west, northwest, east, southeast. And we just published a paper of students, a lot of dikes. So our group, mostly students and me, have measured more than 1,500 actually dikes. You can see from all of the measurements, this pretty strong trend at about 0.35 degrees for a trend. There are a couple of oddballs that have, we're not totally sure what they reflect, why they have such different orientations, or one domain. But overall, again, this would suggest that if this is 0.35 for a trend, then extension at 90 degrees to that in either direction would give you 125 or east, southeast, west, northwest extension of the crust. So the crust is just really being ripped apart. And just to show that with the major strike slip fault, the biggest one that has 150 kilometers of right lateral strike slip, that the extension direction, this is just a textbook figure that have oriented parallel to the main fault, that we would expect dikes to have this orientation and extension in this way. All right, so all this seems to work. And then again, last little bit here is this magmatic flare up. So we have this lull, presumably due to the flat slab, and then this big, these big bodies in orange. These bodies are over 300 square kilometers, at least these, the Cooper Mountain and Golden Horn, are very large volume bodies. There's, in terms of volume, there's 1,800 feet of relief on these. I think even 2,000 up here. This is the one I had that picture of the dike with big hill slope or mountainside. So we have those, and then within this metamorphic complex, there are more magmas. This rocks, or these parts of this underwent high temperature metamorphism. So there's this big thermal input. And so what we think happened, the model we're proposing, is that as Silesia starts to subduct into the trench, basically, once it reaches it, the slab, remember it was rolling back, the slab essentially just tears or breaks off. So the slab starts tearing up because, again, there's no longer a ridge essentially pushing, and there's the slab pull is not sufficient to keep this thing going down. And so what happens is the downgoing plate just breaks up and probably doesn't break off simply, it starts getting torn. And as a result, hot asthenosphere comes up, and this generates a tremendous amount of melting because of the bringing up of exposing this really hot mantle asthenosphere. So this is the model for the Eocene flare-up and why there's so much more magmatism than during a normal arc. I just should point out, it's really interesting from the geophysics is there's something called a slab curtain where geophysically from seismic velocities, geophysicists recognize a big chunk of basalt. When I say chunk, this is Idaho. You can see this is over a big area and it extends almost vertically in the subsurface. And so we think this, Silesia was connected to the slab, and there's still this bit of the slab left that broke off and sunk, but has not reached, but stuck in the Earth's mantle. Finally, one of my favorite units is Skagit gneiss. Here, I just wanted one other aspect of this thermal and a pretty picture is the Skagit gneiss, which are the metamorphic rocks in the North Cascades, or one of the largest groups of metamorphic rocks. It was metamorphosed at about 10 kilobars, so over 30 kilometers paleo, or to about 35 kilometers paleo depth, and underwent very, very rapid cooling, again in the same critical interval, and everything changed. And these are gneisses, but you can see all these white material are partial melted sediments, so there are little bits of melt or magma that came in, and you can see they're kind of folded and contorted. All right, so for the sake of time, let me just make this simple. This is a plot of pressure versus temperature as determined for SK as the Skagit gneiss. And what you'll notice is these rocks were at high pressures and they dropped to low pressures. So presumably they were uplifted or exhumed, in this case by over 5 kilobars, by over 15 kilometers, without cooling, with hardly cooling at all. So near isothermal decompression. And the interpretation would be that this is due to very rapid stripping off of the rock above, much more rapid than, say, normal erosion. And this again fits very nicely with the geothermal chronology, which suggests rapid cooling of these rocks at 49 to 47 million years. And then finally, that brings us up to the time where the rocks start getting too young for me, when they get 40 million or even 45 is pushing it. And here we see what happened. The triple junction had migrated, as I said, so now it's down. Exact location a bit uncertain, but northern Oregon, northwestern Oregon here. Silesia is collided. We have this new subduction zone, and as a result, start back into getting a more normal arc, which is essentially the earliest stages of the modern Cascadia arc, which extends, of course, from southern British Columbia down to Mount Lassen. And the hotspot trace then, at this younger time, it starts, the continent overrides it. So now the Yellowstone hotspot is well under the continent rather than being under oceanic crust. And so after this, then at least for the Pacific Northwest, we're getting much more into what it is today, and will be until the ridge off the Pacific Northwest, and actually it'll collide first down in Northern California and Southern Oregon, since it's closer to the continental margin. But we're pretty similar to what's going on today. So I don't know, there's a lot of text. I think I've kind of emphasized these main points about the influence of having a ridge with an oceanic plateau on it approach the continent. Then the collision, nicely explaining why you have this deformation of the crust in a relatively short period of time, and then this rapid transition in the plate margin with the faults and the dikes and a whole bunch of other things still to the east that I didn't talk about, and this very, very impressive magmatic flare-up, rapid exhumation, presumably uplift of the rocks, and then essentially after the subduction zone jump and the reorganization, which took 5 to 7 million years perhaps, we formed the modern Cascadia system. So lots of things happened. And finally, one of the things that we've thought about and can't think of any particular reason, this period of time was really remarkable, the Eocene. I've already mentioned the collision that started the Himalayas, the big change in the plate motion of the Pacific plate with the Hawaiian Emperor Seamount chain. There was subduction of another ridge in Northeast Asia, the Iceland, I think it's called, probably mispronouncing it, but there were other just dramatic changes in the overall plate configuration, and at about that time. Again, the Earth is not growing, so when you do have a major effect at one place, it's going to influence others as well. Anyway, I think I'll wrap it up there. Thank you for your attention.
Thanks, Bob. So your last statement is related to a question that I was going to ask, which is, I guess I could ask it two different ways. One is, are there places right now on Earth where there are these oceanic islands being driven into trenches, or can you not tell?
As far as I know right now, and I may be doing a mental block, the closest place, but it doesn't have a big, I don't know, the best known place actually is in, I don't have a figure at the end here, but one would be in Chile. So maybe actually, do I have, I'll go back to a map, the beginning here.
Yeah.
Yeah, so if you go, if you go here, you have the situation where the Nazca plate and the Antarctic plate are colliding. It's a little simpler. It's coming. It was very different than the San Andreas system, say, where in terms of the orientation of the ridge. So the ridge here is coming in pretty much at right angles, and the triple junction is migrated from south to north, and it's pretty cool. I was on a field trip there 15 years ago, where you can just look at the volcanism shut off as the ridge comes in, and you can just track it, the ages of the volcanism when it's shut off, going from south to north, and then the reestablishment of arc volcanoes as because it used to be the Nazca plate going off Peru here that was being subducted, and now it's the Antarctic plate, and the Antarctic plate it's reestablished, so you're starting to get new volcanoes. Antarctic plate moves slower, and there is deformation. If you ever, most people know Torre del Paine, but Fitzroy and Cerro, anybody's ever been on the other side there, I think that's where the Patagonia sportswear picture is. There's a nice little fold and thrust belt on the east side of that you drive through as you go to essentially to hike up Fitzroy over here. And so that would be the best example. It's not as, but again, you don't have this big thick plateau on it that's going in. And I say that's the big difference. And Emperor Seamount, that seems to be a little less. There's not a ridge. It's just, and it's definitely subsided. There's some other places in Japan where there are some hotspot things, but they haven't shown the damage that you do here. And I don't know how much of it has to do. I think it's mentioning was this is so young. If this really started, the oldest dated basalts are 56 million, and if it collided at 52, it was still really hot. It was still buoyant, quite buoyant. And I don't know how much of an effect difference that would make.
And let me ask one more question, and forgive me if this is a simple-minded question, but when you had the diagram up that showed the age progression of the Yellowstone hotspot, so I think it looks like, yeah, right there. So am I understanding this correctly, that essentially the hotspot was below what is now Yellowstone 40 million years ago?
No, it's
okay.
The hotspot's here. So these rocks down on the Oregon coast, say at Tillamook, they used to be here.
Okay, got it.
So they've moved. And
I got it backwards.
So similarly, and this also gets, of course, at one thing that we never really know in geology, an absolute reference frame. And that, let astronomers start thinking about the big picture of
right. So
of what an absolute reference frame is. And that's why, the hotspots have always been used. We thought maybe they were fixed, but they're not.
Okay, so all you know
they're
is
not totally fixed, but
all you know is that the hotspot and that crust were lined up.
Yeah.
40 million years, or well, over on the coast, were lined up 40 million years ago.
Yeah. And the hotspot is probably moving very slowly, well, certainly very slowly relative to the plates. And
got it.
Just like if we go to, the Hawaiian situation where it's right here. And so that's why, that's the cool thing about this bend. You can, it really nicely shows that the motion of the Pacific plate changed dramatically. I mean, that looks like
it's like 45
degrees more change trend.
And you can lay down ages on every single one of those islands really well.
Yeah, people dredged you have the islands, and of course, as it thermally as the crust lithosphere cools off and it subsides, and so then they become submarine and seamounts, but you still can image and dredge them.
Right. Very cool. All right. Bill DiVincenzi put a question in here very close to the beginning of the talk. And Bill, are you still on? Yeah, he is. So Bill, why don't you go ahead? I've just turned on your, your ability to talk. So you can go ahead and ask the question yourself.
Okay, you can hear me now?
Yep.
Okay, great. Yeah, I was just, interestingly enough, I just read an article or a science alert about the largest underwater eruption ever recorded. It gives birth to a massive new volcano, and it's by the island of Mayotte, which is off of or between Madagascar and Africa. And this, in the last year and a half, from a flat sea floor, they got almost a 3,000 foot tall mountain, whatever you want to call it. And I was just wondering if you had, if that was
I don't.
part of what you do or not. Yeah.
I wonder which one of the. I wonder if it's one of these two hotspots that are shown. I'm not familiar with that.
Yeah.
There's one between Madagascar and Africa, and then the one right off Madagascar.
I think it's probably the one between the two.
Yeah.
That they're referencing.
No, I am not up on it. I doubt. My colleague Ryan Portner, who studies submarine volcanism, he's in Norway, so I doubt he's here since it's the middle of the night.
Yeah, I don't see his name.
Yeah.
Yeah. Anyway, I just found this fascinating because that you got that much growth in a year and a half.
Yeah, that's hard to believe. That's
well, they say it's the largest ever recorded. So I have to, Anyway, okay. Well, thank you. I just wanted
I'm sorry, I don't have any. You know more about it than I do.
Oh, what that thing says, but okay, thank you.
Yeah.
So the next question was input by Holly-Ann McClure, and Holly-Ann, you should be able to unmute yourself and ask the question live.
It's one of my current grad students. So don't worry.
Hi, Bob. Yeah, so I just had a question about the resurrection plate. I remember you mentioning that last semester, and you mentioned it in this talk, and just that the evidence is given by the on-land geology.
Yeah.
Like, is it similar to what you've described in this talk in Washington and Oregon, or is it something completely different?
No, it's purely based on the on-land geology. So the resurrection plate, if it existed, is gone now. It's named after Resurrection Bay, and which is south of Anchorage. It hasn't. So it needs to be resurrected if we're really going to understand if it really existed, but it's totally subducted. So it's based on the presence of near trench magmas and other evidence here. It looks like right where the Aleutian Peninsula at 60 million. It's a little older. You don't have 60 in Vancouver Island, but again, to explain why at slightly younger times, where basically you have these near trench magmas all along the continental margin.
Okay.
And so if the one way to do that is have a ridge and then this ridge segment come in, right? And that's all going to be getting close at the same time. So it helps to have another plate, but again, that's purely on land geology because it doesn't exist. And the Kula
right, but
plate,
that makes sense. Wanting to,
pretty much gone too. So that's always been the problem going back to when plate tectonics was first being worked out. Is in the East Pacific, we learned so much about plate motion, as you know, from studying the paleomagnetism of the Earth's crust, and so of the oceanic crust. So you've got all this Pacific plate, so you can study well what was happening on the west side of the Pacific, but naturally where we are, it's all gone, right? Most of the Farallon plate off San Jose is not here. And so we're inferring by looking across the ridge and the paleo ridge, and that's why it's there is some evidence from tomography which I don't understand all the physics of it, but you know, again, it's like, we talked about this, but it's like going to the dentist or to a doctor and having someone do tomography on you to find your infections in your sinus infection deep in your head. But there is suggestion that there is a piece of downgoing plate in the right position for the resurrection plate. So, and where
But a
the
lot of the
slab window
evidence is based on those specific types of rocks that you would normally see near the trenches, and you're seeing those on the land.
Exactly. And
Okay.
over a broader area where you're
Okay.
because the argument for those of you, if you look at an area, say like where we live, 100 million years ago, we were essentially a paleo trench. The deposits, you know, the deposits in San Jose, the rocks, many of them. And the geothermal gradients in trenches are very, very low. They're the coldest on Earth because you're taking cold material and bringing it down rapidly, so it chills the overriding plate. And so why would you get volcanoes or intrusions in an area that should be really, really cold? Like I said, like, why do we get, there's something called the Page Mill basalt, Page Mill Road, and that's just a few million years old. Same thing at Coyote Reservoir, east of Gilroy and Morgan Hill, same thing.
Thanks, Bob.
You're welcome.
All right, the next question is from Manny. Manny, you are allowed to talk.
Can you hear me okay?
Yep.
Yeah, I hear you, Manny.
Hey, Bob, I really enjoyed your talk. Thank you.
Thank you.
Can you go back to the slide where you had the hotspots,
Sure.
showing the global distribution of hotspots?
This one?
Yeah, so, you know, I was staring at this and it struck me how uneven the distribution of hotspots are. You know, like Africa's got a bunch, and East Asia and Western Pacific, they don't have any. So why is the distribution of hotspots so unfair?
Well, partially, and again, I think this is my understanding. I haven't really thought about it too much lately, but Africa. The African plate is overall has a higher heat flow because the main way you cool things off, right, is you have subduction. In Africa, if you look at it, right, it's the only plate that it's got a passive margin all the way around it, right? And so until you get up to this little bit where, in Morocco, where you have the collision with the remnant collision with the Iberian Peninsula. And so the thought is heat is not being dissipated efficiently there. And that's why Africa overall is so high. You know, you go to, I remember flying into Namibia, and, you know, you're at flat as a pancake, but you're almost 2 kilometers elevation there. And that holds for a lot of Africa. And even, you know, where it's rifting, and Rwanda actually gets up, not on a Kilimanjaro, it gets up to 19,000 feet in the Rwenzori Mountains. So you basically have a lot of heat. So I would assume that's part of it. It's trapping the heat. That's a really simplistic way of putting it, but that would be what comes to my mind. And is the Pacific, you know, really, and this is something that I don't think anyone has a good explanation for. In the early Cretaceous, maybe 120 million years ago, there is a large volume of hotspot magnetism in the Southwest Pacific. And, you know, if you look at one of those, say, National Geographic maps of the Earth, that pretty standard, and just look at the topography, the seafloor topography, these lots of areas of really high elevation in the seafloor, still underwater, and very large volume plateaus. And for some reason there was a lot of magnetism in a intraplate setting, so presumably hotspot. So again, why I don't think anyone has come up with a satisfactory explanation for that. And that's where one of the Shatsky rise, which we know about, which is what actually was thought to have been broken up and then or broken in half and been subducted beneath California to shut off the Sierras and cause all the deformation. And the reason the Rockies are high in Denver or west of Denver and so far inland and up into or down to Taos and that part of the world is because of this collision of the plateau that presumably was formed down there. So I don't really have a good answer.
Thanks, Bob.
So we have 2 remaining questions. It's about 10 after, so we'll just wrap it up with these 2. Frank Raviola, you are able to talk.
Yes, you hear me?
Yep.
Yeah.
Hey, Bob. So I presume it was just a plate motion at the time, the reason why the way that the ocean plate was moving over the hotspot, why Silesia is north of the hotspot and not on the south?
Yes, because it migrated, it would have migrated because of the reorganization with the right lateral strike slip faults. So I don't know if this shows it, but yeah, this is a little too old, but the basic idea that once Silesia collided, then when the ridge migrated or the triple junction migrated southwards, then it would be getting pushed to the northwest. This maybe shows it better, right? When, if you can see the cursor down here, when the triple junction migrates to the south, and that's going to, the overall motion is going to translate Silesia northwards away from the hotspot.
All right. Great.
Okay. And then our final question for the day is going to be from Steve Brands. Steve, go ahead.
Hi, Bob.
Hi, Steve, long time.
Yeah. So this may be something we have to do in the, in the happy hour, because it's a rather vague question about the absolute references, something that I've thought about, but when you mentioned it, it seems like a pretty serious question for geologists. I became aware of this because we visited Hawaii, and I was in Craters of the Moon, which is of course southwest of Yellowstone, and I've been to Kilimanjaro. I mean, how do we know that the hot spot isn't moving under the surface rather than, at some point there must be a way to determine absolute position relative to the core or relative to the,
Well, I don't, it's, again, you brought up, we do have a sense from, we do have GPS now, so we can certainly say how California is moving relative to Nebraska.
Okay.
And we can do that. And it's really doing the reconstructions between, and this was how it was originally worked out by Dave Engebretson and his Stanford PhD, many, in the early 80s, was to look at, try and pull things back to all the different major hotspots. Mm-hmm. So one way to do it is with a hotspot reference frame. So if the hotspots were all moving relative to each other as well, then it would be impossible really to try and, not impossible, but very difficult even to do the kind of restorations we are doing now. But, the big problem is, let's say India and Tibet, maybe they're both moving northward. It's just India's moving faster. So everything is relative.
So it's all, eventually it comes back to the relative positions of the different hotspots.
Yeah, if you assume they didn't move at all, and that's their way. And I'm not at some of the physics and math is over my head. But it's well, a lot of it's analytical geometry, really, but it's doing these various calculations between, if you say use how everything moved relative to mid-Atlantic ridge to the Azores, and you do it Hawaii, and you do it a bunch of other hotspots,
Yeah.
and you kind of come up by connecting from one to the next to see if it makes sense, and it does broadly make sense that that we can work out a relative motion, but again, it's obviously in the most simplistic way, the Earth, as I understand it, is moving through the galaxy or through the universe, so that gets you even more of a absolute framework question issue, I suppose.
Steve, we have to peg the
Okay.
hotspots to distant quasars. That's how we do it.
Oh, that's okay. That'll do.
All right. Well, thanks, Bob, for a great talk. I think I have more questions that I'm going to send to you. And thanks for those of you who stuck with it to the end. And I hope you have a great Friday. And if you're interested in happy hour, I know Miri sent out an announcement about an hour ago. So take a look and join us if you can. All right. Thanks, Bob.
You're welcome. Good talking to you.